Good morning, elements. Welcome to podcast for review on Unit A. You have taken many multiple choice finals. You've taken many free response finals. At this point, I'm thinking you do have a good understanding and a review of various units. But I thought I'm going to revisit it one more time, unit by unit, to kind of bring all the concepts that you've studied in a unit together. Now, my disclaimer here, I'm trying my best to incorporate most of the concepts. However, some major concepts might be left out. So please go over your PowerPoints and notes and use these podcasts only as a review device. All right, so Unit A. Unit A had 4 chapters in it. Chapter 1 dealt mostly with matter, what is chemistry, branches of chemistry, mixtures, separation of mixtures, and so on. Second chapter went more into naming and nomenclature that came with it. And let me check here. In chapter 2, then we moved on to atoms, molecules, ions, what is our periodic table, and then we talked about ionic covalent compounds, and then rest of the chapter was on naming. Chapter 3 was stoichiometry, where we started talking percent composition and empirical formula, molecular formula, formula for hydrate, and then the last chapter, chapter 4, was on reaction prediction. How do you write balanced net ionic reactions? How do you predict what the products might be? And then we classified them in 5 major types, and then we talked about each of those. So I'm going to kind of bring all the concepts together today for you for Unit A. So Unit A, at the heart of chemistry lies matter. What is the matter with matter? That's my joke for today. So matter is really important to chemists because chemistry is the study of matter and its property. So with the matter, we know matter has properties, and we've studied many types of properties. We've studied physical and chemical properties. Be sure to distinguish between them. So physical properties are the ones that you can observe without changing chemical composition of something, like color, luster, solubility, boiling points, melting points are always physical properties. Chemical properties generally would be reactivity. How does something react with certain chemical, and so on, like would something react with hydrochloric acid? What is its property if you add a base to it, and things like that. And then we also studied about extensive and intensive properties. And extensive properties depend upon the amount of matter, while intensive properties do not depend upon amount of matter. So extensive properties are mass, volume. So the more the matter is packed or present, the more is the extensive property. For intensive property, these are independent of how much matter is present, like boiling point, density. So whether you take 5 mils of water or you take 25 mils of water, it will boil at 100 degrees if it is pure water. So the amount has nothing to do with the property. Moving on here, let's talk about the types of matter. So the types of matter, we have elements, we have compounds, and we have mixtures. Elements are simplest types of substances, and I do call you elements because you guys make up my world in the classroom. So elements are simplest types of matter. These are the ones you see on the periodic table, and currently we have 116 or so elements. Elements cannot be broken down further. So elements unit is atom, and this is the smallest unit that has all the physical and chemical properties of a substance. Compounds are made up of elements like H2O, CO2, and you know the compound, there are two laws that govern compounds. One is law of constant composition. And what was this law? This law had said that if you have a pure compound, no matter where you get it from, you always have the same ratio by, what's the keyword here? Mass. Same ratio by mass. I'm not talking mole ratio. Same ratio by mass of different elements in a compound. And just to clarify, in water, that ratio is 1 to 8, not 2 to 1. 2 to 1 is the mole ratio. The mass ratio is 1 to 8. So if you take pure water from anywhere in the world, if it is pure water, hydrogen and oxygen will combine in a mass ratio of 1 to 8. Then there was law of multiple proportions. And law of multiple proportions applied only to the compounds where the two elements formed more than one compound. Like in case of hydrogen and oxygen, they form water and they form H2O2. You can take NO for example, NO, NO2, and N2O3, N2O5. So law of multiple proportion says with the fixed mass of one element, the mass of other element that combines is in small whole number ratio. So if you look in this example, with 2 grams of hydrogen in each case, 16 and 32 grams of oxygen are combined. And if you look at the ratio of 16 to 32, that's 1 to 2. So with the same mass of one element, the mass of other element that combines is in small whole number ratios. And this is law of multiple proportions. Oftentimes you are asked to do either a multiple choice or a short free response part of it on these laws. So kind of remember these laws. Now moving on from here, we have mixtures, and mixtures do not have always a constant composition, meaning if you were to take a mixture from one part of the world to other part, its composition may vary. Mixtures are of two types: homogeneous mixtures and heterogeneous mixtures. Homogeneous mixtures are also called as solutions, and for that sample, the composition is same throughout. If you were to take a teaspoon of sugar and dump it in water and dissolve it nicely, that makes a homogeneous mixture. You take out teaspoon after teaspoon, it's got the same composition throughout. But if you decide to make this mixture another time, this time you added 2 teaspoons of sugar in the same amount of water. Is the composition of the first mixture that you'd made, sugar water, to the second same? No, it's different because you added different amounts. But for that particular sample, is the composition same throughout? Yes, and that's what makes it a homogeneous mixture. A heterogeneous mixture is the one which does not have uniform composition. So an example of a heterogeneous mixture could be cereal. As you eat Lucky Charms, you know, every spoonful is different. Sometimes you may get 2 marshmallows, sometimes you may get none. So that's an example of heterogeneous mixture. Now from mixture comes separation. You can separate mixture. So another distinction between elements, compounds, and mixtures is mixtures can be separated by simple physical methods. To separate a compound, you need harsher chemical methods, and elements cannot be broken or separated further. So separation of mixture has 5 different techniques, and we talked about each of these in class in detail. Please refer to your notes. Hand separation, and this is a technique you use if you are eating M&Ms. You kind of pick your favorite one first and then work your way through it. The second methodology of separating the mixtures is called filtration. And filtration is when you use a filter paper in a funnel. You take a circular filter paper, fold it in a 3-to-1 manner, you put it in there, and filter paper acts as a sieve, so the thicker particles stay on top while the smaller particles pass through. And filtration can either be used for heterogeneous mixtures or suspensions, but homogeneous mixtures will pass right through it, so it's not used for homogeneous mixtures. I'm going to change the color so it doesn't get too cluttered. The third method of separation is using a separating funnel. And remember, a separating funnel was this kind of equipment, and it is used for separating immiscible liquids. Do you remember that term? Immiscible liquids. And these are the liquids that don't mix with each other. So oil and water is an example. So you can take the mixture, shake it real good, let it stand, and it'll separate out in 2 layers, and then you can separate them. So this is used for immiscible liquids. The fourth method, I'm going to go over here because I've kind of lost room here. So the fourth method of separation is centrifugation. And centrifugation can be used for homogeneous or heterogeneous mixture or suspension. This is based on centrifugal force. So if you have different size particles that have different masses, basically it's mass based. So if you have different mass particles, then they will layer from the heaviest particle at the bottom to the lightest particle on the top, and then by dissolving them in different solvents you can separate them out. And the second to last method of separation is distillation. Distillation is a method that can be used for heterogeneous mixtures or even homogeneous mixtures. So how would you separate a homogeneous mixture? Let's say you have salt water. So you boil it off, the water boils off, leaving the salt behind. You can also use distillation to separate out 2 liquids that have different boiling points. The lower boiling point liquid will boil off first. The higher boiling point liquid will boil off later. And the last method is chromatography. And you've done chromatography in detail in Chem Honors, so I'm not going to go over it, but chromatography again is a method of separation for homogeneous mixtures. You will use a stationary phase, paper, gas, or liquid, and a mobile phase, which is your solvent that you use, and the mixture components separate based on their affinity for the solvent phase, and based on which stationary phase you've used, you can call it gas chromatography or liquid chromatography or paper chromatography. So that's methods of separation. Now moving on to compounds. Actually, let me go back up a little bit. So matter also shows you reactions, gives you various reactions. Now reactions, this is now veering a little bit towards chapter 2. Reactions, we need reaction prediction. And when you write reaction prediction, remember you always write balanced net ionic equations. And for this you also need solubility rules, because you need to be able to predict what will precipitate, what will stay in aqueous solution. And reactions are of 6 types. Actually 6, let's write them, let's list them. So combustion, easiest type to identify because you'll see oxygen there. Decomposition, where one single reactant is breaking into multiple. Single replacement or redox, all single replacement reactions are redox reaction, but not every redox is single replacement. Then the double replacement or metathesis, where they switch partners. And last one is complexation. And maybe I'll do a podcast on reaction prediction, but here I'm going to leave it at that. Please go over each one of these. Now, to be able to predict double replacement or be able to write net ionic, you do need solubility rules. Remember, solubility rules dictate which one will break, which one will not break. Just to give you a quick overview here, when you write net ionic equations, what dissociates? Strong acids dissociate, and how many strong acids you have? You have 7 strong acids. The list is in the PowerPoint if you've forgotten. HCl, HNO3, H2SO4, HCl, HBr, HI, HClO4. So these are your 7 strong acids. Then your strong bases totally dissociate, and strong bases are all hydroxide of first and second group except from beryllium and magnesium. Then all ionic compounds that are soluble will dissociate. So when your solubility rule says it's soluble, you separate it out. Like, and I'm going to elaborate it here, like sodium nitrate. All nitrates and alkali metals are always soluble. So when you write it, you'll write it broken up. There is an exception to it. If the problem says solid sodium nitrate was added, if it says solid, then you don't break it to begin with. You do need water to break it. Anything that forms a precipitate, like silver chloride, will not dissociate. So keep these things in mind as you are dissociating. Now I'm going to move on to matter and compounds. Right here, compounds, you can analyze the compound for their composition. So I'm going more towards chapter 3 now, and I'm going to scroll down, and hopefully I wouldn't lose all that writing. If I do, you do have it in the podcast. So I'm going to do analysis on the next page because I'm out of place here, but in the big concept map, that's where analysis fits. So whoa, it's adding to my PowerPoint. Let's give it 1 minute, and then I'm quickly going to move over to analysis, and I'm going to talk about empirical molecular formulas, then I'm going to talk about percentile, percent error, and determining the formula of a hydrate. So while it is populating this slide, let me go over empirical and molecular formula. Remember, empirical formula is the simplest ratio of elements, mole ratio, not mass ratio, mole ratio of elements in a compound. Glucose's empirical formula will be CH2O, but its molecular formula C6H12O6, where it gives you the exact ratio or moles of each element in a compound. So empirical formula is good just to know what all elements are present in a compound, but for most things you want to know the molecular formula of a compound. So let me just insert, no, let me go to home, new slide, blank, right there, we're good to go. Slideshow from current slide. Okay, so I'm going to continue for compounds, and then I'm going to talk about analysis of compounds. So I'm going to talk about 3 things: empirical formula and molecular formula. Empirical formula is simplest mole ratio, and this is actual mole ratio of elements in a compound. Okay, so glucose has molecular formula C6H12O6, but here this is CH2O. How can you determine empirical formula? You can determine from percent comp. Remember, in this method you assume 100 grams of compound, and then you figure out moles of each element, dividing mass by molar mass, and then you find the simplest whole number mole ratio. These are the steps, and you can look at the PowerPoint for more details. Then you can also find empirical formula from combustion data, and you must go over it from the PowerPoint as well, where typically you burn the compound, and most of the compounds have carbon, hydrogen, nitrogen in it. So if you burn carbon, it forms carbon dioxide, you burn hydrogen, forms water, you burn nitrogen, forms NO2. So they'll give you typically the grams of these, and using the grams of these you can figure out the grams of elements, and then you change it to moles of elements, and from there you find mole ratio. Now the second part here under analysis that I want to talk about is percent error and percent yield. They are two totally different things. The only thing they have common in them is percent. Percent error is how much error is there in your data, and percent error is the absolute value of accepted minus experimental over accepted times 100, while percent yield is actual yield that you got in the lab over theoretical times 100. And the last thing that I want to cover here is formula of a hydrate. And to figure out formula of a hydrate, guys, remember hydrate's a compound like CuSO4.5H2O. Here they will, the methodology here is the compound is heated up, so the water is driven off. You will have mass of water, and you will have, or you can calculate mass of anhydrous compound. When I say anhydrous compound, I'm talking just CuSO4 by itself without water. And then you can change mass of water to moles of water, and you can change mass of anhydrous compound to moles of anhydrous. Anhydrous means without water. You can pull down the stool, it's okay. Anhydrous compound. And then from here, basically you got to figure out in 1 mole of anhydrous compound how many moles of water are present. And I have sample problems for each of these in your PowerPoint, so if you need further clarification, please look at it. So that is a really short, concise review of Unit A. I haven't done reaction prediction here. I might do it later, or I might address that in class. Thank you for listening.